All right, guys, now it's time to get into some fun stuff, to the good things. A little bit of new today, actually, probably a whole bunch of new material for you. So, what we're talking about today is normal distributions, which you may have heard referred to as a bell curve in the past. But what we have right here are two examples of a normal distribution. So, what a normal distribution looks like, and we had mentioned this in a video before. The reason they call it a bell-shaped curve is because you've got one side is a mirror image of the other side. So if I go right down the middle here, the left and the right are mirror images of each other, and there's a single peak up here in the middle, and then it kind of slopes off as we go further away from that middle, and that gives it that kind of bell-shaped. So the difference between these two, they're both bell or normal distributions. The one on the left, though, has a larger standard deviation. So the data is a little bit more spread out. So it's still the shape of a bell. It's still a normal distribution. It's just a little bit wider. Whereas this one on the right, the data is a lot more clumped together. So you still get a normal curve with a peak in the middle. It's just a taller peak. The data is all more close together. Okay. So depending on the data, you don't always get a normal curve. Okay. So for example, here on the left, we've got the chest, and I don't know where they come up with this stuff, the chest circumference of Scottish militiamen. So this is how far around you can measure the chest of a Scottish man in the militia. And you kind of see this bell curve, right? You see it go up in the middle and then kind of taper off on the left and the right. Now, this one maybe isn't a perfect normal distribution. It looks pretty close. There's a peak in the middle, and then these ones on the right are a little bit higher than the ones on the left, but it's near a normal distribution. Whereas this one on the right-hand side, the population density of 50 states, so you have a whole bunch of states where the people are spread out. And then you've got a couple states where there's a lot of people clumped really close together. And then you've got all this in the middle. But this one doesn't have that normal curve. If I were to follow this data, this one is skewed to the right because of all of these really densely populated states, these outliers over here. All right, so for a distribution to be considered normal, these are just kind of four of the conditions that it meets. So most of the data is clustered in the middle, giving the distribution that single peak. Okay. 2 says that the data values are spread evenly around the mean. So it makes it symmetric. In other words, this one, we've got a peak, but the data values are all spread to the right. There's no data getting spread evenly to the left. And our example here on the left-hand side, the data on the right's a little bit higher. That's why we're saying it's near normal. It's near a normal distribution because the data is spread out pretty evenly, but not perfectly, of course. Number 3 says larger deviations from the mean become increasingly rare. In other words, the further I go out from the middle, from my mean, the less occurrences I have. Okay. And that gives us this tapering that happens at the end. It gets really skinny and not a lot of instances happen. And then number 4, the individual data values are usually a result from different factors, okay, such as genetic and environmental. So things like height, like weight, cars being produced, there's all these different factors that go into it that give it this normal distribution, okay? So example 2, which of the following variables would you expect to have a normal distribution or nearly normal? So A says scores on a very easy test and foot lengths of a random sample of adult women. So if I think about the scores on an easy test, that means I'm going to get a lot of people. Like if I draw those scores right here, let's say this is 0% and this is 100%. If it's an easy test, I'm probably getting a lot of people up here in the high scores. And then I probably don't have very many low scores. Now, here's the problem with this test, is it maxes out at 100. So if it's an easy test, a lot of people are getting these high scores, but you don't have all these people tapering off to the right. That's not happening. So this one is skewed to the left, mostly because of that 100% maximum amount right there. So that one wouldn't be a normal distribution. Foot lengths of randomly selected women is probably going to be normal, okay? Unless you're in Wyoming, because those girls all have giant feet. Anywhere else, it's probably going to be a normal distribution. Approximating areas. Okay, so again, we're approximating, so our numbers aren't exactly right, but there's this rule called the 68-95-99-7 rule. And that's one that you're going to want to memorize. That's one that you're going to want to have down by the end of this. Now, what this says is if this is my normal distribution, okay, right here in the middle, I've got my average, I've got my mean right here. And then as I go to the left, if you notice down here at the bottom, it says -1 SD. Now that SD stands for standard deviation. So if I'm 1 standard deviation away, I'm right here. If I'm 2 standard deviations away, I'm here. And then same thing going to the right. If I'm 1 standard deviation higher than the average, we're here, and 2 standard deviations. So what this is saying is if I have a normal distribution, then 68% of my data is going to fall between -1 standard deviation and 1 standard deviation from the average. Okay, 68% of my data is going to be right here in the middle. So what that means is I'm going to have 34% in this group on the left and 34% in this group on the right. Okay, then it goes on to say within 2 standard deviations, I'm going to have 95% of my data. Okay, 95% of my data should be within 2 standard deviations on a normal curve. So half of 95 is what? 47.5, but 34%. So on this side, I've got 47.5% that goes from 2 standard deviations all the way to the mean. But 34% of them are already in this group, which leaves me with about 13.5% in this gap and 13.5% in this gap. And I would write these down. This is a picture that you're going to use a lot today. So put that 68%, copy this diagram down, because then we go on to say within 3 standard deviations to the left and 3 standard deviations to the right, 99.7% of the data is going to fit within that range. So we're only going to have 0.3% of the data floating around out here, which means that I'm going to have about 0.15% on this side and about 0.15% on this side outside of 3 standards. So between here, let's see, we went up what, 4.7. So this is going to be 2.35% of the data. And this is going, let's use a different color right there, 2.35%, which means this gap has 2.35% of the data. Okay, so 68% of our data is within 1 standard deviation. 95% is within 2, and 99.7 is within 3. And those, we're rounding the numbers a little bit. It's actually 68.3 and 95.4. For the sake of this assignment, we can go ahead and round those decimals. So example 3 says the test that makes up individual parts of the SAT are designed so that their scores are normally distributed. So that means I know I'm going to have this bell curve, and there's a mean of 500. So 500 is going to be right here in the middle, and a standard deviation of 100, and a range from 200 to 800. So interpret this data. So what that means is I've got my curve, And right here in the middle, I've got my average score of 500. When it says the standard deviation is 100, going to the left, looking at my example here, if I go down 1 standard deviation, that means this is 400 because each of my standard deviations is 100. And if I go up one standard deviation, I go up to 600. So 68% of my data is between 400 and 600. Okay. But then if I go another standard deviation, now I'm at 700, and over here I'm at 300. So that means this is my 95% group. 95% of people score within 300 and 700. And then if I go 3 standard deviations out, if I go all the way out to my third, this is 800 and this is 200, and 99.7% are going to fit within those two values. Okay. So what that looks like when it's drawn professionally and not by your math teacher is this. You've got your average in the middle, and then 1 standard deviation to the right. Since each standard is 100, we go up by 100, up by 100, up by 100, and then we go down by the same amount. Okay. Now we're going to have to use this diagram to do a lot of math going forward. So example 4, vending machines can be adjusted to reject coins above and below a certain weight. The weight of a legal US quarter is normally distributed. So that means the weight of the quarter is going to have that normal curve, okay? And that's about as normal as we're going to get. And it has a mean of 5.67. So 5.67 is right here in the middle. And a standard deviation of 0.0700 grams. If a vending machine is adjusted to reject quarters, okay, so before I finish, I'm going to draw my picture. While I've got this number in my head, this 0.07, that's my standard deviation. So 1 standard deviation to the right, I've got to add 0.07. So this is going to be 5.74. And 2 standard deviations to the right is going to be 5.81. Now going to the left, 1 standard deviation, I've got to minus that 0.07. So I'm going to get 5.60. And then to go 2 standard deviations, I minus 0.07 again, and I get 5.53. Okay, now I'm all right with my picture. If a vending machine is adjusted to reject quarters that weigh more than 5.1, so it's going to reject all of these quarters out here, and less than 5.53, so it's also going to reject these quarters, what percentage of legal quarters will be rejected? Okay, looking at this picture, I know that 65% land right here, right? If I go back to my diagram, 68%. If I look at my diagram right here, I'm just going to copy this information over to here, right? So my 68% are in this group. And then my next 2 standard deviations out is my 95%. Okay. And that's my limits. That's my limits right there. So 95% should fit within this range of weights, which means that it asks what percentage are going to be rejected. Well, 95% are going to be accepted. So the rest, the 5%, are going to be rejected there on the outside. Okay. Example 5, a survey finds that the prices paid for 2-year-old Ford Fusion cars is normally distributed with a mean of 17,500. So here's my distribution. My mean is right here in the middle at 17,500. And there's a standard deviation of 500. So that means 1 standard up is going to be 18,000. Another standard up is going to be 18,500. And another standard up is going to be 19,000. And going to the left, 1 standard deviation down is going to be 17,000. 2 standard deviations is going to be 16,500, and 3 standard deviations is going to be 16,000. Okay. Consider a sample of 10,000 people who bought Ford Fusions. Okay, I'm considering it. Part A, how many people paid between 17,000 and 18,000? Well, 17,000 is right here. 18,000 is right here. And I know that this group right here is 68% of my people. And if I know that there's 10,000 people, I can take 10,000 and times that by 68%, which if I'm doing that on my calculator, I'm going to do 10,000, 1, 2, 3, but I'm going to times it by 0.68. So 6,800 people paid between $17,000 and $18,000. Okay. This is the percent that paid that amount. This is the number that fits that percent. Okay. How many paid less than 17,000? Ooh, this is a good question. Because I know that this amount right here is 34. We decided that to get from here to here, let's go ahead and copy in our information. We've got 13.5 and 23, or 2.35. So this is 13.5, and this is 2.35, and this is 0.15. So there's a few different ways that we can do this. What I want to know is this batch right here. How much of the data is that data? And I can cheat a little bit because I know that from here to the left is half of the data, right? And I also know that this little piece right here is 34% of the data. So rather than adding these ugly decimals together, I'm just going to take 50% and I'm going to minus this group right here, the 34%, and I get 16%. About. So 16% of 10,000 people. Again, on your calculator, make sure you put that in as a 0.16. So 1, 2, 3 times 0.16. We're going to get a nice number. So 1,600 people paid less than 17,000. Okay. So you're going to have to do some problem solving with these. You're going to have to look at the diagram and kind of break down what you know about it. How many people paid more than 19,000? So 19,000 is right here. So it wants this group to the right of 19,000. Well, I know, let's see, we've got from 3 standard deviations to 3 standard deviations is 99.7% of the data, right? So that means that this little 0.15 and this little 0.15 is all that's left. So more than 19,000 would be 0.15%. So I've got to take that 0.15 and times it by 10,000. So again, we're going to do 10,000. Now here's where we're going to be careful because we're timesing by 0.15%, which is 0.0015. And you're going to get 15 people. 15 whopping people paid more than $19,000. I don't know why they would. If the average was only $17,500, that's quite a bit higher than the average payment. All right. Okay, moving on. Standard scores. Okay, so the number of standard deviations that a data value lies above or below. So far, what we've just been using is we've just said 1 standard deviation, 2 standard deviations, 3 standard deviations, right? We haven't been using anything but those exact 1, 2s, and 3 standard deviations. But the truth is, a lot of values aren't exactly 1 standard deviation away or 2 standard deviations away. They're somewhere in between those nice, beautiful numbers, right? So to figure out how many standard deviations away a value is, that number we call a z-score. Okay, a z-score is how many standard deviations away we are. So for example, The z-score for this right here is -1. You are -1 standard deviation away. -2 standard deviations away, all right? But there's a lot of in-betweens. So the way that we find that value is you take your data point that you're interested in, you subtract whatever your average mean value is, then you hit enter on your calculator so that it does this correctly. Then you divide by the standard deviation. And that will tell you not how far away you are, that will tell you how many standard deviations away you are. And we're going to use that number a little bit later, okay? So for example, the standard score of the mean is 0 because the average is 0 standard deviations away from the mean. The standard score of a data value 1.5 standard deviations above means 1.5. 2.4 standard deviations below means -2.4, okay? So for example, IQ scores. The Stanford Binet IQ test is scaled so that scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the standard score. So find the z-score. I wish it used z-score more than standard score for IQ scores of 85, 100, and 125. So I take my data value, 85, and I minus the 100, and then I divide by my standard deviation, which is 15. So this becomes -15 over 15, which becomes -1. So 85 is -1 standard deviations below the average, okay? 100, well, because that's the average, I know that the z-score is 0. If I take 100 minus 100 and divide by 15, that's 0 divided by 15, which is 0. And I know that because that's the average score. It should be 0. Now, if I take 125, I'm above the average, so my answer should be positive. And this is going to become 25 over 15. And we'll go ahead and turn that into a decimal because we've got 5/3. But let's turn that into an exact value, 1.666666 forever, right? So that would be my z-score. I'm 1.66666 standard deviations above the average, okay? Now remember, a standard deviation is the average distance away, okay? So if you have a standard deviation or a z-score of 1, if you are 1 standard deviation away, you are average. You are the average distance from the average score. I know that's a lot of averages in one sentence. You are the average distance from the mean, from the middle number. If you are more than 1 away, you are further away than the average person. If you are less than 1 away, then you are closer than the average person. Does that make sense? This -1 score is kind of the average distance away because it's just 1 standard deviation. All right, percentiles. So the z-scores kind of coordinate with a percentile. So looking back at our diagram, it's really easy to say that if I'm right at the average, if I'm right here in the middle, I'm in the 50th percentile. I'm right in the middle. I'm higher than 50% of the people, okay? If I go up to this value, if I'm 1 standard deviation higher than that, then I'm at about the 84th percentile, meaning I am above 84% of everybody else. So that percentile correlates with a z-score, okay? Because depending on how many standard deviations away you are, you're going to be a certain percentile. You are going to fit at a certain percentile. You are going to be above everything below you a certain percent, right? So here's the table. So if I have a z-score, look right here in the middle. If I have a z-score of 0, I'm in the 50th percentile, which is exactly right. You are right at the average. If your z-score is 0, you are average. If you have a z-score of 1, then you are in the 84th percentile. So you are higher than 84% of everybody else. Okay, you're in the 84th percentile. And that's what percentile means. So if I find out that, hey, you know what, I'm at negative 1.3, so I'm in the 9.68 percentile, that means there are 9% of the people below me, and 81% of the people, or 91% of the people are above my score. Okay. So example 7, cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. In what percentile is a 20-year-old man with a cholesterol level of 190? So the first thing I need to know for percentile is the z-score. All right, so if I'm at 190 and my average is 178 and my standard deviation is 41, so I'm going to take 190, I'm going to minus that 178 and hit enter, and then I'm going to divide by 41. So my z-score is 0.293. Okay, so if I go and look for that here, and it's a positive 0.293. 0.293 is at about 0.3. So that means I'm in the 61, 62 percentile. All right. What cholesterol level corresponds to the 90th percentile? Ooh, I like this question. All right, so I don't know the cholesterol level. So I'm basically looking for this number right here that correlates to a percentile. Well, the 90th percentile, where is that? 90th percentile is right here. So to get in the 90th percentile, you need a z-score of 1.3. So if I want my z-score to be 1.3, to get my z-score, I take the number I'm looking for, I minus the average, and I divide by the standard deviation. Usually we're looking for the z-score, but now I'm looking for the value. So I'm going to go ahead and times that 41 over, and then I'm going to add the 178 so that I can figure out what x is. So let's do 1.3 times 41, hit enter, 53.3, and then I'm going to add 178. So 231.3 is the cholesterol level that corresponds with the 90th percentile. So if you have a cholesterol of 231, you have a higher cholesterol than 90% of everybody. That seems like it's a pretty high cholesterol. I would imagine that's not a very good thing to be one of those people. Example 8. The heights of American women ages 18 to 24 are normally distributed with a mean of 65 and a standard deviation of 2.5. In order to serve in the U.S. Army, women must be between 58 and 80 inches tall. What percentage of women are ineligible to serve based on their height? Okay, so if I'm at 58 inches, if I'm looking, there's a couple of different ways that we can do this. And because 58 isn't an exact number of deviations away, I need to find my z-score. So I'm going to take 58, I'm going to minus the average, and I'm going to divide by 2.5. Okay. So if I take 58 and I minus the 65 and get negative 7, and then I divide by 2.5, I get negative 2.8. Okay. So that's my z-score for the short. Okay. Now the z-score for the tall people, 80 inches. So if I take 80 minus 65 and divide by 2.5, so let's go ahead and go 80 minus 65, enter, divide by 2.5, and I get 6. So my z-score for the tall group is 6. So if I look at what I'm looking for is what percentage of people are too short and what percentage of people are too tall. So a z-score of negative 2.8 puts me right here, okay, at the 0.26 percentile. So 0.26%, and it's not in decimal form, right? Nope. So 0.26% are too short. Now, for those that are too tall, if I look at a z-score of 6, look, that's not even on the chart. And that's because there really is, there's not very many people that are going to be that tall. 80 inches, that's a really tall human right there, right? That's a 7'8" person. So to be 80 inches, there are very, very, very few people, which really isn't even going to be a percentage. We're not even going to count that percentage. So really, the percentage of American women that are ineligible is just that group that's too short, because the too tall group doesn't even exist. So we're only worried about 0.26% that are too short to enter the military. All right, so this is going to be homework 6C. Now, I know it's new. I would start on all of these problems, draw the distribution, okay? Don't be lazy. Draw that normal distribution, label the mean, label your standard deviations. Remember to go to the right, you add each standard deviation, you go left, you subtract, and use that diagram to help you problem solve through the homework. If you have questions, I know you're doing this at home. You're not able to come into class and ask because it's fall break right now, at least if you're taking this in the fall. So if you have questions, please email me. I usually can respond to you within an hour or two. I'll get back, and hopefully I can help you with whatever it is that you ran into on that problem.